Hello, everyone, and welcome to the VaNTAGe seminar. So we're continuing our series on lean in algebraic number theory and arithmetic geometry. And today for our talk, we're very happy to have María Inés de Frutos-Fernández, who will be speaking about local fields in lean. And María, is it all right if we record this talk?
Yes, that is correct.
Oh, great. And if you have questions, feel free to ask them during the talk. Okay, María, please go ahead.
Hi, thank you very much for the invitation to give this talk. I'm going to discuss a formalization of local fields in the lean theorem prover, and this formalization is joint work with Filippo Nucchi. I'm going to split the talk in 4 parts. So in the first part of the talk, I want to talk a little bit about lean and the mathematical library Mathlib. And I'm not going to spend a lot of time on this because probably many of you already saw Alex Best's talk last week where he provided a very nice introduction to lean. But I still want to say a few words in case this is the first time that you are seeing lean. Then I will discuss discrete valuations, fields with a discrete valuation, how they are related to discrete valuation rings. And in the next section, we will specialize this to local fields, and we will see some definitions and some theorems related to local fields. Finally, in the last part of the talk, I will spend a few minutes discussing future work, because the main goal that Filippo and I have in mind is formalizing the proofs of the main theorems of local class field theory. Okay, so starting with the first part, lean, the system that I'm going to be using today, is an interactive theorem prover developed by Leonardo de Moura in Microsoft Research since 2013. And it has a quite big mathematical library, a unified mathematical library called Mathlib, which is created by the community. So there are around 300 contributors to Mathlib, many of whom are mathematicians. Just to give you an idea of the size of the library, a couple of days ago, the statistics were that we had around 77K definitions, 140K theorems, and around 1.5 million of lines of code. So lean uses type theory instead of set theory, but for the purposes of this talk, you can mainly ignore this. So whenever you see type, you can replace it by set in your head. So whenever you see the notation lowercase t colon capital T, this means that T is a term of the type capital T. And you can translate this in your head as T is an element of the set capital T. There is a special type for propositions, which is called prop. You might see the function notation used at some points in this talk. So we use fun x maps to f of x to define the function f of x in lean. And something that it's also a bit different about this system is that it allows us to use mathematical notation as part of the language. So common symbols like the notation for the natural numbers or the periodic numbers for all exist. These are things that can pretty much be used within the language. To give you an example, here I am defining the square function on the real numbers. So this is the function from R to R that sends an element x to the element x squared. I also want to mention that lean can keep track of mathematical structures and objects. So for example, here I am defining a set G, and I am imposing a commutative group structure on G. So these two blocks are saying that G is a commutative group. And then the next two blocks are saying that T is a topological space. Now, once we have set up these variables, lean is going to be able to access the structure associated to these objects. So for example, here, if I have two elements, G and H in this group G, I can prove that G times H is equal to H times G, because lean already knows that G is a commutative group, and therefore this is a true statement. To prove theorems in lean, we normally use tactics, which are commands that tell lean what we want to do in a proof, what is the next step that we want to do, or what are some instructions that we want to follow. And this can be some very specific talks about very specific tactics about what to do in the next step, or it can also be more general tactics that can do like several steps in the same instruction. So for example, here, I want to prove some statement about propositional logic, and I'm doing that by constructing the truth table using the tactic Tauto. And in the next line, I want to prove this formula for the square of a sum, and I can do this using the tactic ring, which uses the properties of commutative rings. And sometimes we may also write proofs without actually using tactics, and you may see some proof like this in this talk. And we normally do this when the proof is very short and we can write it in like 1 or 2 lines without actually having to do many steps or using tactics to help within the proof. Since you have seen that the mathematical library is quite big at the moment, it is important to be able to search effectively inside this library so that you know what is available and what you can use in your formalization work. There are different tools that you can use for that. So there is the math documentation. There's also the idea that we try to follow a naming convention where the names of the definitions and the theorems are descriptive. And then we have websites like Moogle and Loogle that you can use to search in this documentation, and also some tactics that can help you do that. And finally, if everything fails, you can go to the Solid chat of the Lean community, and you can ask the experts there to see if something that you need is already formalized in the library. In today's talk, I'm going to be talking about local fields. And by local field today, I mean a non-Archimedean local field. So I'm going to be excluding the real numbers and the complex numbers. I'm only going to focus on the non-Archimedean case. And my definition of non-Archimedean local field is going to be that this is a field complete with respect to a discrete valuation and with finite residue field. Now, in fact, most of the theorems that I'm going to discuss today don't need the full strength of this definition. So many of the results that I will discuss are true without assuming that the residue field is finite. And also some of them are true without assuming that the field is complete. And in Lean and in this mathematical library mapping, we try to follow the philosophy of formalizing everything in the correct degree of generality. And we try to do the same in this project. So anything that works in greater generality than for local fields, we have tried to formalize in the correct degree of generality. And that's why the second part of the talk, it's not going to be local fields, it's going to be about discrete valuations. Before getting to that, I'll give you some statistics about the project so that you can get an idea of the size and the complexity. So this project took us about 8,000 lines of new code. This code was first formalized in Lean 3 because that was the version of Lean that was in use when we started the project. But since then, the community has moved to the Lean 4 version. So we have translated everything in our project from Lean 3 to Lean 4. And the examples that I'm going to be showing today and the code snippets that I'm going to be showing are already in the Lean 4 version of the code. I will say that some of them are edited a little bit for simplicity. So if you want to see the actual code for everything, you can do that by clicking the link in the last slide of the presentation. Something that is very important is that for this project, we needed to use results from several areas of mathematics. We needed results from algebra, topology, analysis. And for us, it was very useful to have a unified library like Mathlib, where all of these results are available, and it is guaranteed that it's going to be relatively easy to interact with different parts of the library. Besides the library Mathlib, our project is also based on a previous project of mine, which is available in this link. Okay, so let me start with the formalization of discrete valuations. I will try to be very precise about which things were already in Mathlib and which things we are adding in our project. So the first thing that I'm going to discuss is the definition of valuation. And this might not be the definition that you are expecting to see. So the definition that I'm going to give is that a valuation on a ring R is a map V from R to gamma naught, which is a linearly ordered commutative group with 0, that has the properties that the valuation of 0 is 0, the valuation of 1 is 1, the valuation satisfies the strong triangle inequality, and the valuation is multiplicative. Now, probably this is what you will call a multiplicative valuation or an absolute value, a non-Archimedean absolute value. And in many cases in pen and paper mathematics, you, instead of working with this definition or on top of working with this definition, you might also want to work with the definition of additive valuation. The reason we are going to use this one today is that this is the definition for which we have more API on Mathleaf. We have more lemmas and more results available. So our life will be much harder if we try to work with the additive version of the definition. So we will be working with multiplicative valuations essentially everywhere. And then once I have ring R with a valuation, I'm going to define the unit goal of this valuation as the subring consisting of elements with valuation less than or equal to 1. Now, an example that all of you will be familiar with is the p-adic valuation. So to construct this, I start with the ring of integers, so R is equal to Z. I start with a prime number P, and I start defining the additive version of the valuation. So for me, the additive p-adic valuation IP of a non-zero integer R is going to be the maximum N such that P to the N divides R. Of course, every power of P is going to be by 0, so in that case, I'm going to say that the additive p-adic valuation of 0 is equal to infinity. Now, this can be extended to an additive valuation on Q, just by saying that the additive valuation of a fraction is the additive valuation of the numerator minus the additive valuation of the denominator. And well, here you have some examples. So 18 is equal to 2 times 9. So the three-adic valuation of 18 is equal to 2. And similarly, the three-adic valuation of 5 over 27 will be negative 3 because the valuation of 5 is 0 and the valuation of 27 is 3. Okay. Now, whenever you have an additive valuation, you can construct a multiplicative valuation from it following this kind of process. We are going to define a map BP from the rational numbers to P to the Z union 0 by sending a rational number X to P raised to the negative of the additive p-adic valuation. Now it can be checked that this satisfies the properties of being a multiplicative valuation on Q. One technical detail about the formalization is that in Mathleaf, instead of taking P to the Z union 0 as the codomain, we are going to take an abstraction of this, which is denoted ZM0. And this is a type that we construct first by taking a multiplicative version of Z. So essentially, this is like taking P to the Z, but without actually having to choose a base P for this exponential. And then once we have this multiplicative version of Z, we add it a 0 element with this class with 0. Okay, so whenever you see ZM0 in the stock, you can replace it in your head, if you like, by P to the Z union 0. Okay, so valuations were already formalized in Mathleaf, but discrete valuations were not. So this is one of the first things we added. We added the definition of discrete valuation. There are a few different ways that we could have done this, but we chose to say that a discrete valuation on a field K is a subjective valuation taking values in this type with 0 multiplicative set. A possible alternative would have been to say that a discrete valuation is a valuation taking values in ZM0 without requiring that valuation to be subjective. However, then we will have to deal with with equivalent valuations, and this is something that we want to avoid. So we will always be working with the normalized discrete valuation. And this is just the code corresponding to this definition. We have a valuation on a field K taking values in ZM0. And the class is discrete, is just a proposition, is the proposition that the valuation map is subjective. Some examples of discrete valuations will be the p-adic valuation on Q or the x-adic valuation on the field FQX of rational functions of FQ. one reason that discrete valuations are nice is that they have uniformizers. So a uniformizer for a valuation V on a field K is an element pi of the field which has additive valuation equal to 1. So if you are thinking about the example of the p-adic valuation, having additive p-adic valuation equal to 1 is equivalent to having multiplicative valuation p to the negative 1. This is why here in the formalization, you see that to be a uniformizer, we ask that the multiplicative valuation of 1 is this multiplicative of add of negative 1. So you should replace this in your head by p to the negative 1. And we provide two versions of this definition. So the first version is just a proposition, is uniformizer, so that given an element of K, you want to say that you can use this to say that the element is a uniformizer. But then there are other situations where you actually want to fix a uniformizer and you want to work with it. And we provide a bundle structure to do that. So in this case, this structure consists of two fields. The first one is val, so this is going to be an element of the field, which is in fact an element of the unit ball of the field, so we have defined it that way. And then a proposition that this element val is a uniformizer for the values. We prove that a valuation V on a field K is discrete if and only if there exists a uniformizer for V. So we do this in two steps in the formalization. So here I am declaring the variables, K, the hypothesis that K is a field, and V, which is a valuation on K with values in set and 0. I'm setting up notation K naught for the unit ball of this valuation. And then I'm splitting the proof of this statement in two parts. So in the first part, I assume that I have a uniformizer pi for the valuation, and then I conclude that the valuation has to be discrete. And in the converse lemma, I assume that the valuation is discrete, and then I am able to prove that there is an element of the unit ball of K, which is a uniformizer for the valuation. The next result that we want to prove related to uniformizers is that if pi is a uniformizer for a valuation V on a field K, then any non-zero element R in the unit ball of K can be written in the form x is equal to pi to the n times u, where n is some natural number and u is some unit in the unit ball. So this is formalizing this lemma here. So we fix a uniformizer pi. We fix a non-zero element of the unit ball, and then we conclude that there is a natural number n and some unit in the unit ball such that R, I'm calling it R here and X here, but it's supposed to be the same thing. So R is equal to pi to the n times u. Something that we can conclude from this factorization is that the maximal ideal of the unit ball is actually generated by any uniformizer of the valuation. Okay. Now we have talked about discrete valuations. Now I'm going to talk about discrete valuation rings. Discrete valuation rings were already defined in MATLib. There are a few equivalent ways of defining discrete valuation rings in the library. This is the main definition this is the definition that is called discrete valuation ring. So we say that an integral domain is a discrete valuation ring if it is a local principal ideal domain, which is not a field. You can also find some equivalent definitions in MATLib. However, all of the definitions that you can find there, none of them refer to discrete valuations because discrete valuations were not available in MATLib before our project and are still not available in MATLib. So something that we did in our project is we want to relate this notion of discrete valuation and the notion of discrete valuation ring. So the first theorem that we prove is that if K is a field with a discrete valuation V, then the unit ball K naught is a discrete valuation ring. This is the proof of this theorem, this proposition. So really the only part that is a bit more involved to prove is the first part, the part that the unit ball is a principal ideal ring. But this follows essentially from this discussion about the uniformizer generating the maximal ID. And then the other two properties are very easy to prove. This one is inferred by Lin immediately, and this one is just a couple of techniques. And then we can also go the other way. So we can start with a discrete valuation ring A, and we can put a valuation of the fraction field of A and show that this valuation is discrete. So the way we do this is we take the valuation generated by the maximal ideal of A. This gives us a valuation on the fraction ring of A. This is something that I had done in the past, and this is available in Mathiv for any dedicated domain. So in particular, we can use it here. And something that is new to our project is the proof that this is actually discrete. But essentially, this follows from the fact that we already knew in Mathiv that these kind of valuations have uniformizers. Okay. So, okay. For the next couple of slides, I want to assume something else. I want to assume that K is complete with respect to a discrete valuation. The first result that I want to prove is that if K is such a field, and then L over K is a finite field extension, then L has a unique discrete valuation W that induces V, and moreover, L is complete with respect to this valuation W. This proof is, in some sense, split into parts. So in the first part is to prove that L has a unique valuation W prime that extends the valuation V. This means that for every element X in the field K, the valuation P of X is equal to the valuation W prime of X. Of course, if we want to do that, the price that we have to pay is that the codomain has to get bigger. The codomain cannot be equal to set M0 anymore if we want W prime to actually extend V. So we do this by saying that W prime is a valuation taking values in the non-negative reals. This first line of the proof is something that I had done in the previous project about norm extensions. So I proved that this is the case, not just for discrete valuation, but more generally, this is true for rank 1 valuations. So this was already proven. And now the issue that we have now is that we don't want a valuation that takes values in the non-negative reals. We want a valuation that takes values in set M0 and is moreover normalized, right? So informally, what will happen here is that we actually know that the codomain is not the full non-negative reals. This W prime is actually going to take values in some smaller ring, in some smaller set, which informally you can think of as the Q roots, the Q powers of set M0 for some rational number Q. However, this set M0 to the Q that I'm writing here, this is not a type that makes sense, right? Because you cannot really take the Qth power of an element in set, of a term in set M0, where Q is a rational number. So I'm just pointing this out to make clear that in the formalization we have to do a bit more. So in the informal argument, you just say, okay, we know that W prime takes values in this set, and therefore we can renormalize it to make sure that it takes values in set M0. And if we are a bit careful, we can actually show that the normalization that we choose is surject. In Lin, this argument that seems very trivial in the informal mathematics, it is a bit more involved because we have to be very careful about which type we are working on all the time. So if you want to see a description of the argument, this is explained in the paper that Filippo and I wrote. Okay. The next theorem that we prove for fields complete with respect to a discrete valuation is that if we have, again, such a field K and an extension L over K, which is finite, then the integral closure of the unit ball K naught in L is actually equal to the unit ball L naught. In particular, this means that this integral closure is again a discrete valuation ring. So this is done in two lemmas. So in the first lemma, we are proving that the integral closure this will be K naught. So this will be the integral closure of K naught in L is equal to the unit vol of L with respect to the extension of the valuation. And then in the next instance, the next lemma, we saw that therefore this integral closure of K naught in L is again a discrete valuation ring. The next few results have to do with completions. So again, now if we start with the decaying domain R, I'm going to assume that R is not a field because Mathlib's definition of the decaying domain includes fields, but I want to exclude them for this definition. So R is a decaying domain, K is the fraction field of R, and then P is a maximal ideal of R. We already knew, it was already available in Mathlib, that then the completion KP has a discrete valuation that extends the valuation VP associated to this maximal ideal P. So this part was already in Mathlib. However, we are now, thanks to our work, we are now able to conclude that this the unit vol of this KP naught, is going to be a discrete valuation P. So let me show you a little bit what the code for this looks like in Lean. So here I'm setting up the variables from the previous slide. So R is a decaying domain. K is a field, which is an algebra over R, and I am assuming that K is isomorphic to the fraction field of R. And then V is going to be some, I'm saying that V has type height 1 spectrum of R, so this is saying that V is a maximal ideal of R. And then I set up some local notation, so RV is going to be the integers of the V-adic completion of K, and KB is going to be the V-adic completion of K. So yeah, these first two definitions we could already make with what we had in Mathlib. We already had available this lemma that there exists a uniformizer for this valuation. And we added proofs that the valuation on KB is discrete and that therefore the unit vol RB of this valuation is a discrete valuation. Now, normally, when we work in informal mathematics, we identify two different definitions on KP. And we want to be able to do this in Lean as well, but we have to be a bit careful. So the first definition that I have showed you in this previous slide is that if we start with K and with this prime P of R, then KP has a valuation that extends the valuation on K. This is the valuation that I showed you in the previous slide. And I'm calling this the completion of adic here. So this is one way to define the valuation on KP. However, we now know, well, Lean now knows that KP naught is a discrete valuation ring. And therefore, we have seen that we can endow in KP, which is isomorphic to the fraction ring of KP naught, with the adic topology generated by the maximal ideal of KP naught. And I'm calling this valuation adic of completion. So I'm calling it that because first I am completing KP and then I'm taking the valuation generated by the maximal ideal of KP. So something we did is we proved that these two valuations are actually equal. So they agree on all elements of the field KP. So we can again identify them when we are working on Lean. Even though definitionally they are not equal, propositionally we can show that they are the same values. Okay. So now that we have set up the general theory for discrete valuations and discrete valuation rings, we can specialize to construct the definition that I showed you at the beginning of the talk, the definition of local field. So I had said that non-Archimedean local field is a field complete with respect to a discrete valuation and with finite residue field. So to do this in Lean, we fix a type K, which is a field and has a valued instance. So this means that it has a valuation from K to set M0, and I'm assuming that the topology that K is endowed with the topology induced by this valuation. And then I have to impose 3 conditions on this data. So the first condition is that the field K is complete for this topology. The second condition is that the valuation HV.V, so the valuation on K, is discrete. The last condition is that the residue field of K is finite. So HV.V valuation sovereign, this is the unit ball of the valuation associated to K. And I'm taking the residue field of this unit ball, and I'm asking for this residue field to be finite. Okay. Now we know that local fields can actually, well, non-Archimedean local fields, of course, can be of 2 kinds, mixed characteristic or equal characteristic. And there are some situations where we might want to treat these 2 cases separately. So besides formalizing this abstract definition of local field, we also formalize the 2 more specific definitions. So I will start with the mixed characteristic case. We define a mixed characteristic local field as a finite field extension of the field QP of p-adic numbers for some time. So in Lean, we fix some prime number P and some field K, which is an extension of QP. And then we have to ask that this extension is finite dimension. This is how we write the definition in Lean. The first thing that we prove, or one of the first things that we prove, is that this definition is actually a special case of local field. So whenever you have a mixed characteristic local field K, you can conclude that K is a local field in the sense of the previous slide. If you're somewhat familiar with the MathLib library, and especially with the p-adics in the MathLib library, you might have noticed that I'm using a notation here that is not the standard notation for the p-adics in MathLib. And this is because we are using a slightly different definition. So in MathLib, the p-adic numbers are defined like this. So the p-adic numbers are the Cauchy sequence completion of Q with respect to the p-adic norm. And then the p-adic integers are defined as the subtype of the p-adic numbers, consisting on elements with norm less than or equal to 1. We decided to use a definition which is mathematically equivalent to this, but is not exactly the same definition. So we set up QP, Q underscore P, to be the adic completion of Q with respect to the p-adic valuation, and then set P to be the unit ball of this, the unit ball of QP. So why did we do that? So why did we do something different instead of using the MathLib definition for the p-adic? Well, one reason is that this adic completion definition here, this is something that works whenever you have a Dedekind domain R and some maximal ideal in this Dedekind domain. And sometimes we want to talk about, we want to use this to construct, for example, completions of a completion of a local field. So the problem if we use the MathLib version of the p-adics as the base case for mixed characteristic local fields is that then we will be using 2 kind of incompatible definitions, because in one case we have this Cauchy sequence completion, and in the other case we have this adic completion. It is a bit easier if we are using the same construction everywhere. A second reason why we decided to do something different is that in the MathLib definition of the p-adic integers, they are defined just as a subtype And then that means that you have to do a bit of work to show that this is actually a subring and to get some properties that you might want about this ring. By contrast, we have defined set P as the valuation subring of QP. And this has the advantage that then we can use all of the API that is already available in Mathlib for valuation subrings. So in particular, if we define set P this way, we don't have to prove that this is a ring, this is going to be automatic, and we also get other things for free, like for example, the fact that this is going to be a local ring. But of course, we want to make sure that everything that we are doing is still compatible with Mathlib. So a way we did this is we provided isomorphisms between our version of the p-adics and Mathlib's version of the p-adics, and same for the p-adic integers. Okay, now, given any mixed characteristic local field K, we define the ring of integers of K as the integral closure of set P in K. And yeah, this is just this line here. So this is the integral closure of set P in K. So again, I am using our definition of the p-adic integers instead of Mathlib's definition. And thanks to the general theory that we have developed for discrete valuations, we already know that this ring of integers is going to be isomorphic to the unit ball K0 of K. And in particular, we get for free that this is a discrete valuation ring because we have proven it in greater generality. Okay, we also did the equal characteristic case. So an equal characteristic local field is a finite field extension of the field FPX for some prime P. So FPX here is defined as the completion of the field FPX of rational functions over FP with respect to the maximal ideal X generated by X. So this is the corresponding Lean code. So again, we have to fix a prime number P and a field K. We now assume that K is an algebra over this completed field FPX. And then we ask that this extension is finite dimension. Same as in the mixed characteristic local field case, one of the first things we do is we prove that this satisfies the definition of local field that we saw at the beginning. In the case of the equal characteristic, there's also something that I also comment about our choice for working with FPX completion. So the type FPX completion that I'm using here in the definition is the added completion of the field of fractional function over FP with respect to the ideal generated by X. And analogously, I'm going to define FPX in completion as the unit ball of this field FPX completion. Often in mathematics, it's more convenient to work with the identification of this field FPX completion with the field of Laurent series over K, over FP. And this is something that we have done in general for any field K. So for any field K, we provide an isomorphism between the field of Laurent series over K and the field Kx constructed as the x-adic completion of the field of rational functions. Okay. And as we did in the mixed characteristic case, we can now define the ring of integers as the integral closure of power series in K. But again, keep in mind that this is not actually defined as power series, but we have shown that this is isomorphic to the ring of power series. And we again get for free that the ring of integers is a discrete valuation ring. Are there any questions so far?
Oh, it sounds good.
Okay. Yeah, so then I will say a bit more about future work. So this project, formalizing local fields, for us is the beginning of a proof of the main theorems of local cluster theory. So this is the goal that we have in mind. But when we started this project, we could not even state the phrase let K be a local field in matrix, so we had to start there. But in the last part of the talk, I want to say what our goals are for the future and how we are planning to get there. So the first big goal that we have is proving the local reciprocity law theorem. So this says that for every local field K, there exists a homomorphism called the local Artin map or local reciprocity map from the units of K to the absolute Galois group of K with two properties. So first, for every uniformizer, we have the property that this homomorphism PK applied to pi restricted to the unramified, the maximal unramified extension of K. This agrees with the Frobenius morphism. And then we also want some compatibility condition with finite extensions. So if L is any finite abelian extension of K, then we want to see that this map phi sub K induces an isomorphism P sub L over K from this quotient of the units of K by this norm group to the Galois group of L over K. So in particular, to be able to do this, we need to show that this norm group of the units of L, this is contained in the kernel of this map. So this is our first main goal. And then once this is proven, we will also like to prove the local existence theorem. So quickly, this says that a subgroup N of the units of K is a norm group if there is a finite abelian extension L over K that has the norm group of the units of L are isomorphic to this group N. And the statement of this theorem is that every open subgroup of finite index in the units of K is actually a norm group. But for now, we are focusing on the first theorem. So this is what I'm going to do now. I'm going to discuss our strategy for getting there. And I will discuss some of the ingredients that we need, and I will say a bit about which of these ingredients have been formalized already and which are things that we still have to formalize. So the first thing that we obviously need is we need to develop group cohomology and Galois cohomology. So group cohomology is already available in MATLib, and this is thanks to work of Amelia Livingston. But Galois cohomology is still missing. So this to-do list here, this is taken from the MATLib documentation. Right? So there's some nice things that we would like to have for cohomology. So for example, some API for cohomology in log degree would be nice to have, lone star sequences, and very interestingly for us, we will like to have the definition of finite cohomology so that we can define Galois cohomology. We will also need some facts about the cohomology of the units of a local field. So the first result that we need is Hilbert's theorem 90. So this tells us that if L over K is a finite Galois extension, then this first cohomology group is trivial. And this is not in MATLib yet, but this has been formalized in by Amelia Livingston. So this is something that we will be able to use when we need it. But then we also need some information about the second cohomology group. Right? So we want to show, and this is the theorem that we are focusing on at the moment, that for every local field K, there is a canonical isomorphism in K from this second degree cohomology group of the Galois group Kx over K with coefficients in the units and the quotient of Q by Z. And moreover, this isomorphism is compatible with, again, with finite Galois extension. So if L over K is finite Galois of degree N, then this inf K induces some isomorphism between this Galois group, this cohomology group, and this quotient of this group, which is isomorphic to Z mod N, is a group cyclic of order N. So this is one of the goals that we are focusing on right now. And to get there, we are focusing first on the unramified case. So we are working on formalizing some of the theory of unramified extensions of local fields. So we want to show that if K is a local field, then for every natural number n, there is a unique unramified field extension of degree n, and that this extension is going to have a cyclical group generated by Frobenius. That is what we are working on formalizing right now. Okay. Now, what else will we need? So we are also going to need Tate cohomology. So yeah, so if G is a finite group and M is a G model, we define the Earth cohomology group. So this is going to be an extension of cohomology from now, instead of just allowing R to be a natural number, we are going to allow it to be an integer, right? So the way we do this is if R is positive, this is going to be equal to the Galois cohomology group. And then we extend it somehow into a cohomology sequence that goes to the negative integers, right? So to do that, we have to define the 0 and -1 cohomology as these two quotients. And then for any negative R less than -1, we are going to define it as a homology group. In particular, we will be interested in this Tate cohomology group of order -2, because this is going to be equal to the first homology group. And this is just the abelianization of G. So this is the case that will be more interesting to us to prove local classical theorem. So once we have the definition of Tate cohomology formalized, we want to prove this theorem of Tate that says that if G is a finite group and M is a G model, such that these two properties are satisfied. So for all subgroups H of G, we have that the first cohomology vanishes, and this second cohomology is cyclic of order equal to the size of the group H. Then for every R cup product with a generator of the second order cohomology group is going to give us an isomorphism between HR, HTR, sorry, and HTR plus 2. This isomorphism only depends on the choice of the choice of generator for this cohomology group. Why do we want to formalize this? Well, because if we specialize the case of R is equal to -2, G is the Galois group of finite Galois extension L over K, and M is equal to the units of a field L, then that case recovers the local reciprocity law. Okay, I think this is everything that I wanted to discuss today. So if you have any questions now, I'm very happy to answer. And you can also check out all of our code in this link, this GitHub repository, and also there is a paper describing this work that is available at this link. Thank you very much for your attention.